Hi all, Dr. Clark here again. Today for Gen Bio lecture, we're going to talk about the flow of energy. And in general, we're really just going to talk about what energy is. What is energy to a biologist and kind of the properties that energy has. Okay. You can see here this diagram is a protein, it's an enzyme, and you can see the activation sites or active sites on this protein with the binding molecules bound to it. So this will play a much bigger role. We'll introduce enzymes in this lecture, but this will play a much bigger role when we start talking about how enzymes work in next lecture. Okay, so first of all, most of you know a lot about energy or a lot of basic information about energy. I mean, you are a living organism and you know, consume energy constantly. Okay? But you've also learned about it probably in middle school and high school and things like that from a basic level. Energy is the ability to do work. What does work mean? Well, it can mean a lot of different things. So it can mean, flexing muscles, firing nerves. It could be, more general. It could be capturing prey, the act of eating food, these kind of things. Um, this is all work or work related, and energy is utilized to do those things. I mean, you can also think about it in your general sense, maybe not from a biological standpoint, but from just a general sense, the ability to pick up a bottle and things like that. And you're not talking about the muscle movement, but that's where biology comes in. Okay? Um, so when we look at energy, we need to think about the states of energy. Okay? And it comes in two general states. Kinetic energy, which is the energy of motion. Okay? And we won't talk a lot about kinetic energy, mainly because we, we, we're just not going to talk about animals in motion or things in motion that would have energy. Um, Kinetics and animal kinetics and things like that. Physics is really interested in kinetic energy and things like that. Just in this course, we're not really going to address that very much. We're going to address mainly potential energy. So what is stored energy? Where did the stored energy come from? Where does it go? So these kind of flows of energy from potential energy into kinetic energy, and we'll talk about that. But what forms do potential energy? How's it changing over time? There is a third energy that some people like to put, and they call it chemical energy. But really, chemical energy and potential energy are the same thing. It's stored energy. Now, there are lots of ways at which you can look at the connection between potential energy and kinetic energy. And when a living organism does this conversion, we call it a transformation. So they transform potential energy or stored energy into kinetic energy. And we'll look at this a little bit, okay? But we're going to look at the process by which they make that transformation. Okay? That's the important piece. Okay? And so most of you probably had some kind of physics, environmental science, intro to science course in your life. And you probably remember a simple diagram like this. Potential energy is this ball on the hill. Kinetic energy is the actually ball when it's moving, okay, because it's energy of motion. But I want you to think about it with a kind of a different understanding than maybe you've thought about it before. Okay? Potential energy is stored energy. Kinetic energy is energy in motion. But no matter what, even if it's potential energy here, you have to supply a little bit of energy to potential energy in order to get kinetic energy. Okay? And so you can see here this ball on top of the hill. Okay? Yes, some reactions happen spontaneously and you don't need to supply energy. But most of them you have to supply a little bit of energy to get a lot of energy from that reaction. These are the reactions that we're going to look at primarily in this course. Okay. So the interesting thing about energy, and probably the most convenient thing about energy, is that energy has lots of different forms, okay? Whether that be motion and chemical bonds and even photons and things like that. But all the energy that we know of and all the different forms and all the different types of chemical bonds and things like that, um, they all can be converted into heat. Okay? And old school ways to do this would be burn whatever material you're interested in a bomb kilometer. Okay, and so they used to be just be referred to as, oh yeah, you just burn it in a bomb. Okay, and basically what it is a chamber that is sank down into water. Okay, and the material that you're interested in knowing how much energy that material houses. So this is to look at bond energy or potential energy. That material would be inserted in and lit on fire, burnt in some way, okay? And the amount of energy transferred to the water would be the amount of energy that was housed in that object. Okay? So probably the most convenient and best way to represent energy is to represent it in the form of heat. Okay? And that's why we have terms like calories, which is an actual term for how much heat change an object has. Okay? So if something has 2,000 calories, if that object that you're eating, like a triple, cheeseburger with 4 pounds of bacon, I don't know how much 2,000 calories would be, but you'd probably be pretty close if you ate 3 patties of beef and 5 pieces of cheese and maybe 10 pieces of bacon, something like that. You'd probably be pretty close. But regardless of that, let's say you're not very close, it doesn't really matter. If you burn that down, okay, and it's transferred as heat, okay, then we'd say, well, there's a certain number of calories, maybe 2,000 calories in that item. That's the heat transfer, okay? And that heat transfer of energy is called thermodynamics. Now, it's rare to ever see anyone burn food anymore, but this is the old way that things were done. Now there's a much more convenient way that you can just look at bonds and things like that and get a a more of a theoretical energetics from what is that item made of, because we've done enough burning of things. Yeah. But there are some bombs that are still around in physics and chemistry departments that still sometimes get used in labs and things like that. Okay. So the energy that we're most interested in from a biology point of view is the energy from the sun, because it can be deemed as free energy. Okay? There's no currency, there's no price to pay in absorbing photons that are already coming to the planet from the sun. Now, we'll get into this, but only about 1% of the photons that hit the planet, 1 to 2%, are utilized by photosynthetic organisms. Okay? So there's, 99% of the energy is reflected back or absorbed in the rocks, in the water, things like that. So, when we talk about free energy, at least when I say it's free energy, there's a lot of it out there, okay? And can be utilized to construct bond energy, and then other organisms can consume that. And that's the whole process behind photosynthesis and cellular respiration. Okay? So that's that utilizing photons, utilizing energy from the sun, which allows plants to build potential energy or chemical bond energy, and then to later utilize that to drive other processes or for other organisms to consume that plant and drive their processes. And this goes all the way back to when we were talking about chemistry in chapter 2. Chemical reactions are really the driving point of this energy conversion. This energy is bound up in chemical bonds, normally covalent bonds. That's where the energy is really at, typically. But it's this breaking of the bonds that's going to release energy. And this is really based on thermodynamics. Okay? Most of you know the first law of thermodynamics. Okay? That is, the amount of the energy in the universe remains constant, and therefore energy cannot be created nor destroyed. Okay, so often you'll hear me make a mistake when I'm lecturing about things like photosynthesis or cellular respiration, and sometimes I'll say, and plants created energy, or and this is the process by which ATP is created. Okay, when I mean created in that aspect, all I'm saying is it's formed. Okay, it changes its shape. It might be now in a better storage mechanism, but energy is not created. It might be borrowed from the sun, so that organisms can make carbohydrates and then break those carbohydrates down to do work, and that energy is released back as heat to the atmosphere and then escapes the planet, etc., etc., etc. It's a giant cycle. No energy is created nor destroyed. It just changes form. Right? So it changes form. That's important to know. Another piece that's important to know is that each conversion of energy is lost. So that initial absorption of photons by plants is the best conversion. Right? That's like a 1-to-1 conversion, excellent conversion. Then after that, when the plants break it down, a little bit of energy is lost to heat and waste and things like that. Then when an animal eats the plant, more energy is lost. And this is called the 10% rule. Actually, 90% of the energy is lost between conversions. Only 10% remains. So then, that animal, maybe it's a deer or something like that, ate that plant. It gets 10% of the energy that the plant had stored, that the plant got. Okay? So the animal has to eat, the deer has to eat more plants, then that plant had to borrow photons. Then that deer might be consumed by a human, a wolf, a cougar, whatever it might be. It doesn't really matter. It's consumed. There's another 90% loss of energy, 10% remains. Okay? And this goes on and on and on. Every time you convert, energy is lost to the environment as heat, but also as waste products, and it might escape as poor ability to digest those things. So in some cases, the herbivore that's eating the plant, they might not be able to break down the cellulose in the plant cell walls. So a lot of that's going to go to waste. Decomposers will take care of it, but the organism that originally ate that is not getting that energy. All right, that brings us to the second law of thermodynamics. This is one that most people don't know. Okay? And that is that this disorder will continuously increase in a closed system. Or in other words, this is the second law of thermodynamics, is the entropy law, or basically entropy increases. Entropy is a measure of disorder in the system. So for example, some of you probably had this happen. Okay? It happened to me when I was younger. I'd have a nice clean room, and by the end of the week it would look like this. I'd be like, what happened? Someone destroyed this place. When in actuality, clearly it was me. But even in a situation like this, even if no one ever entered this room and we close this system off, right, entropy would occur. Eventually the sheets would start to deteriorate, the wood would deteriorate, okay? All these things would start to break down over a long period of time, but entropy would increase over time. So what this means for biological systems is that you can't have a closed system. You have to have energy being entered into the system constantly to maintain stability. So it's true that entropy over a long period of time will happen. Things will fall apart, things will dissolve, these kind of things. But in systems where energy is being supplied, that energy, some of that energy is being utilized to maintain order, maintain a system that is not falling apart. We'll come back to this because this is one piece that some critics of evolution have an issue with. Okay? And we'll come back to this and check this out. All right, so chemical reactions, when we're talking about that bond energy or that potential energy, it really starts with reactants or substrates. So it starts with a starting material of something that's going to bind together. And we call these substrates or reactants. When you bond them together, we call that a product. And there are two main types of reactions. Endergonic reactions. These are reactions that energy has to be supplied in order for the product to form. These are reactions that do not form spontaneously. And these are typically energetically expensive reactions. So it takes a lot of energy to get the reaction to occur, and then you have this product afterwards. Okay? But the product is often a very good energy storage molecule versus exergonic reactions. Exergonic reactions don't really have to supply much energy, and the product is releasing energy, so the reactants have more energy than the product. So when the two reactants come together, the energy is released, okay? And this will occur spontaneously. All right. Now some of you remember, and some of you might have done this lab already, where you're adding, liver and hydrogen peroxide, and you got a reaction, an enzyme reaction, and you felt the glass tube that it was in, and it warmed up. That is an exergonic reaction. That means when those two substances come together, that energy is being released. More energy is being released than energy supplied. Endergonic reaction is more energy being supplied than energy being released. Okay. Now, in order for these reactions to occur, we've talked about this before, and we just talked about it, a little bit of energy has to be supplied. Even if it's an exergonic reaction, a little bit of energy has to be supplied. This is called activation energy. So the amount of energy needed to get that bond to form or break that bond or whatever it might be. And this works because the energy needed, or the energy comes in and it disrupts the chemical bonds that are in existence. This might be one product, so let's say, this pen is a product, and it might be enough energy for the product to unravel, right? And for pieces to break off. Okay? So that's just enough energy to break that chemical bond or to destable the chemical bond. It might just cause the shape of the product to change, or the shape of the substrate to change, so water can bond to it and break it apart. Another thing is, though, you could be wanting to put two things together, two substrates together, and the activation energy is needed to disrupt the edges, or maybe the hydroxyl groups or hydrogen groups on each end, so you can get a hydrogenous or dehydration reaction to form one product. Okay? But no matter what, a little bit of energy is required. As the activation energy decreases, so the amount of energy needed for the reaction to occur, as it decreases, the likelihood of a reaction becoming spontaneous increases. In order to do this, we can add something like a catalyst or an enzyme, okay, which will speed up the reaction, but it speeds up the reaction by changing the amount of activation energy needed. So we often, and most people know this, and they've heard enzymes before, enzymes speed up reactions. But how do they speed up reactions? It's by decreasing the amount of energy needed. And in some cases, enzymes are so good at this that there is no energy, really minute, undetectable amount of energy needed in order for the reaction to occur. Other times, the reaction would not occur at all because the activation energy needed to get that reaction to occur is so great that a spontaneous reaction is not likely to occur in anyone's lifetime. So a catalyst has to be used in order for that reaction to occur. Here you can see what I'm talking about. Inorganic reactions. You have to supply energy. Okay? It's a big activation energy curve, and the product is way up here in the energy outcome. So basically how much energy is stored is way up here. Sometimes you have to supply more energy than that can be stored, and other times it's more like a straight line here, and the energy supplied is just absorbed by the product, and now you have this product. Here's an exergonic reaction. Same kind of curve, so you might have to supply a large amount of energy, but you'll get to the peak and then it'll crash, and the product will release a bunch of energy. Okay. And so you'll release more energy than you put in. In this case, you put in more energy than that is released. Now what happens when you add a catalyst, an enzyme? You decrease the amount of energy needed to go to product. Uncatalyzed is way up there, catalyzed is down here, and in some cases it's nearly a straight line down because there's so very little energy needed to get it to go to product when an enzyme is in the mix. All right. So that's really kind of the nutshells of kind of how energy flows. Next, we're going to talk about how enzymes work specifically to catalyze reactions. Okay? And that's next lecture.